Our fourth stage is the memory stage. To a first approximation, it's another simple stage. All we have to do is read or write from memory. So we're clearly going to need to use memory. We need to use val-e that we got out of the ALU because that's how we do address calculation. And then most of the time, we're going to write val-a into memory because that's how we do register to memory operations. But there's a class of operations where we're going to need val-p. And I'll let you think about that while we start to do the implementation. Now, because our diagram's starting to get cluttered, when I add new signals, I'm going to add them in red, and then I'll turn them blue as we add new signals. So recall that we use the ALU for address calculation, and after that, val-e contains our address. So clearly, that's going to need to go into a logic block that tells us where in memory we are reading or writing data. Let's take the case where we're going to write something into memory. Then the question is, well, what are we writing into memory? Well, in that case, we used register RB and val-b to do address calculation. So it was the contents of val-a that we're going to write into memory. So we're going to grab that signal and send it into the data logic. Now we can't let it go through the ALU because we need to use the ALU for address calculation, and we can only use the ALU once per instruction. So we're using it for address calculation, so we're going to grab the signal before the ALU to go into data. Let's think about the inverse operation where we are taking a value from memory and moving it into a register. Again, we're going to use val-e for the address, but now we've done a read in memory, and we're going to call the output of that read val-m. And what happens to val-m is that ultimately it's got to get written back to the register file. Okay, so now the question is, how do we know when we take this value and we send it to the register file, like which register do we need to write it to? Well, in the instruction, it started out in RA, but how do we get that information to the register file? Well, we're going to introduce a little piece of logic that we're going to call dest-m. And dest-m is logic that calculates where, i.e. what register, are we going to use to hold the data that came from memory. So the inputs to dest-m are usually source A, or I'm sorry, RA, because the move from memory to register instruction uses RB for address calculation and uses RA as the destination register. So we'll feed that into dest-m, and then we'll also feed in the opcode so that dest-m can decide when it needs to activate the memory port with the value from RA. Now that takes care of our memory to register instructions and our register to memory instructions. But what about our push and pop operations? Because they too read and write from memory. So how are we going to implement those? Well, we need to figure out where the address comes from, and we need to figure out where the data comes from. So recall that when we do a push, we decrement the stack pointer first and then move data in. But when we do a pop, we read from the location the stack pointer is referring to and then change the stack pointer. So what that means is that for the push operation, we need to go through the ALU and actually decrement the stack pointer. And so we'll use the same address line that we used for the register memory operations. But for pop, we need the value from the stack pointer before it goes through the ALU. It still needs to go through the ALU because it's going to need to be incremented by 8. So we're going to steal the signal out of val-b and say that's the address that we're going to use for pop operations. And once again, in order to decide which of these two addresses we're going to use, val-e or val-b, we need to get information from the opcode that's going to allow us to make that decision. So the data for a push still comes from val-a. When we do a pop, we're reading data out of memory. It goes into val-m. It too will come into the memory port, And, well, we have the information that tells us which register it's going into because it happens to be RA. So we've got enough for push and pop. When else do we need memory? Oh, right, call and return. So let's look at how we might implement those. Okay. Where's the address coming from? Well, fortunately, the address is the same as we used for push and pop, because when we do a call, we push a value onto the stack, and when we do a pop, we pop it off the stack. So that's the good news. The bad news is that the data values are now different, because when we do a call, what we're really doing is pushing the value of the address of the next instruction. Well, where do we get that from? Aha, that's exactly what we calculated when we incremented the PC. So we're going to take val p, direct that all the way over to the data, and say sometimes the data that we want is coming from val p. Now that we have two choices for this logic block, we're also going to need to take the opcode in here so we can decide which ones to use. Okay, we're close, but when we do a return, okay, so what does a return do? It basically pops a value off the stack, returns it to val m, but instead of writing it to the register file, where does it have to go? Well, it actually has to go into a piece of logic that is going to calculate what the next instruction is. And so be patient, we will get there. I just realized I backed up. We'll get there, but we're going to delay until we actually get to the last stage where we compute the next PC, and then we'll figure it out.